All right, here is a possible synthetic target, and we're going to use the same rules as before. We can use benzene, and we can use any alcohol, monoalcohol, from 1 to 5 carbons. So if we add carbons to our growing molecule, we can add between 1 and 5 at a time using these rules. And this basically is just to make it a little more interesting and prevent us from saying, I'm going to buy this product here from Aldrich and that now I'm done with the synthesis. So it just makes us be a little more cognizant of the different synthetic tools that we have available to us. So let's take a look at this molecule. We've got an ester here, which is interesting because as of this video, we have not yet encountered the carboxylic acid derivatives chapter, so that's kind of interesting there. We've got a 4-carbon chain with a ketone kind of near the end, and we have a meta-substituted aromatic ring. So I think the first thing I want to think about is making this ester. There's really only one way to do that, and it is one of my favorite reactions in the aldehyde and ketone chapter. And I'm going to go down for now. I'm going to use my retrosynthetic arrows. And I can make that ester via a Baeyer-Villiger reaction. And that is going to insert an O into the side of a ketone. If we take a look at this molecule, there are 2 ketones here, so we're going to have to be careful about that because the Baeyer-Villiger does react with aldehydes and ketones, and it really isn't going to make any difference between these two. So unless we protect one of them, we might get reaction with both. So let's take this ketone out and protect that. I'm going to make it into a cyclic acetal for now, but I might want an alcohol maybe eventually. We'll see what happens. So going further back, if we observe that this is now a meta-directing group, and of course I can install that with the 3-carbon acid chloride, maybe that's the first thing I do in this synthesis. So let's focus on this chain now. How would I install that chain into the meta position? Well, if I had, probably could install 2 carbons twice, because this is a 4-carbon chain. If I use an epoxide, I can put a nucleophilic position on this carbon, and then I can add acetaldehyde, a 2-carbon aldehyde. So let's look at that possibility. And again, I might have to go back through my synthesis and assess whether I need a protecting group. But if I had this, I would then need a protecting group on my ketone, so let's put that in. But if I had this Grignard, I could react it with this aldehyde to come up with an alcohol that I could either protect or immediately convert to a carbonyl and protect that. The problem is if I have both of these protecting groups on the molecule at the same time, I can't really take them off sequentially or at different times. They're both coming off together. So I think what I want to do is I want to convert this into the alcohol after I add the Grignard. But then I want to leave that as an OTMS protecting group so that I can play with the carbonyl over here and then essentially expose the alcohol and oxidize it to make this carbonyl. So let's look at the next previous step. How do I get the Grignard there? Well, and again, I'm going to protect this or keep it protected. If I have this Grignard and I have an epoxide, a couple steps later I could ring open the epoxide and then I could convert that primary alcohol into a Grignard here, so that would allow me to add the 2 carbons there. So I think I like this target, and that one comes from, of course, the bromine here. So I could take this compound, protect the carbonyl, create the Grignard, and get here, and eventually follow myself back up to the desired product. And I can get here, of course, via bromination of the carbonyl species, and I can get there from benzene and the acid chloride. Problem here is I might not yet know how to make the acid chloride, so I'll show you a couple ways to get to this carbonyl species. So let's go ahead and work from the beginning. Of course, we know that if we have the acid chloride, aluminum trichloride will give us the aromatic ketone. To get to the acid chloride, I need to oxidize the primary alcohol. And I can do that through Na2Cr2O7, H2SO4, H2O. That will give me the carboxylic acid. And then carboxylic acids plus SOCl2 in pyridine will give you the acid chloride. So that's one option. The other option is to take the aromatic ring, convert it to a Grignard, and then I can react it with, let's say there's a Grignard right here. I can react it with the aldehyde, followed by acid, followed by the Swern, and that will reoxidize the primary alcohol that forms here. So we have a couple of options to get to this aromatic ketone. Either one is fine with me. It's just that we haven't really read about this option yet if you haven't read the carboxylic acid derivative chapter. Let's keep going then. We have our aromatic ketone. Of course, we know how to add bromine. This is a meta director, so I can get that to add meta. And then, in order to create the Grignard, I want to first protect my ketone. Then second, I want to add the Grignard. Then I can add the epoxide. That gives me a primary alcohol. I'm going to protonate the primary alcohol. This is mild acid workup. If you'd prefer, you could use ammonium chloride, and that will basically do the same thing, but it would be less prone to removal of that protecting group in the acidic conditions. Once we have the primary alcohol, PBr3 can change that to the bromine, magnesium, so I have my Grignard reagent right here. Then of course I can react that with my aldehyde, so I'm going to do that over here to give me a little more room because I need to make the aldehyde. PCC plus ethanol, so that's the first step. Second step would be to TMS chloride, probably is all we need to do here. We don't even need to make the OH, we could just use the O- and protect that straight away. To make this arrow a little more clear, and let me erase this other arrow which is confusing me. Okay, and so I've added the first two carbons, I've added the second two carbons. Now I have the TMS group, which will not react with the Baeyer-Villiger conditions. And so I'm going to, first step is MCPBA, where the peroxy acid will attack the ketone. We get migration of one of these groups, and remember that the phenyl ring, along with secondary carbons, are more prone to migration than primary carbons. So I'm going to exclusively install the oxygen between the ring and the carbonyl. So now I've created my ester, and that's all I have to do is just MCPBA. It's very simple. Then I need to deprotect with tetrabutyl ammonium fluoride, and I need to then work that up probably with a little bit of acidic condition, so ammonium chloride will allow me to protonate the oxygen. Now I have an alcohol there. I'm going to use the Swern reaction to oxidize that alcohol to a ketone. So that is the sequence here. We've got a couple options to make this intermediate given our current state of knowledge, so either one of them would be perfectly acceptable even on the upcoming exam or on a worksheet. And you see that we've added a couple of small carbon pieces as we go along. This strategy was necessary over here to end up with the functional group on the third carbon of the chain. If it was on the first or the second, we could just maybe use an epoxide or an aldehyde straight away, but we needed to sort of grow our chain a couple times in order to get our function group out here. All right, let's take a look at this interesting synthetic target. There's really only one place of interest, the alkene. The other thing is that we have a cyclohexane ring, which is not an aromatic ring. Be aware that this is not benzene. This is a cyclohexane ring. It's got lots of hydrogens on it. But we're not allowed to start with rings of 6 carbons unless they're benzene. And I'm not really sure how to make a 6-carbon ring very easily. But we also observe that we have sort of 1,4 substitution here, almost as though it were a benzene ring that was para-substituted. So let's think about making this from benzene. What if, let me get back to my retrosynthetic color here, what if this was benzene and we just hydrogenated it to create this product? You can hydrogenate benzene. It takes a lot of pressure and probably some heat, and of course palladium and hydrogen. It just takes a lot more effort than hydrogenating a standard double bond. Something I notice here is that if I wanted to hydrogenate this blue structure to make the black product, I'm probably going to lose this alkene as well. So let me fix that. Instead of having the alkene there, what if I had an alcohol? Maybe not in that position, because I think it would be hard to get my alkene in the right spot. So let's put the alcohol right here. So if I had the alcohol there, I could reduce my aromatic ring and produce the alkene as my final step. So I'm not sure if I can make that, but let's give it a try. Okay, so I put the alcohol here so that I could get regio control over the elimination. I can make the more substituted alkene easily when the alcohol is here. If the alcohol were right here, I would have a couple of equal probability regioisomers, and I couldn't control that. So I think what I'm going to do is actually install that alcohol from the alkene that we started with, and I'm going to make that alkene from a Wittig. So remember that we learned about Wittigs in the aldehyde and ketone chapter, and they allow us to put alkenes exactly where carbonyls were. So that is 100% regio control, which is very useful. So I can use a 2-carbon Wittig to add an alkene to this position, and then I can put my alcohol on the outside of the alkene so that eventually I can re-establish that alkene. This is almost a protecting group for this alkene right here. Making this should be no trouble. I think most of us have seen this a couple different iterations, either in the aromatic chapter or perhaps even on the previous question. This can be made from isopropyl benzene, which is a ortho-para-director, and the bromine. I could turn that into a Grignard, and I can use this aldehyde and then oxidize it once further to get there. And of course I can make the aldehyde from the alcohol. I can make the para-bromo isopropyl benzene from isopropyl benzene, and I can make that from benzene. So let's go ahead and fill in the forward steps here. This is simply, I can make isopropyl chloride from SOCl2 and isopropanol. Pyridine comes along as well. That's a Cl, and that's AlCl3. And then I can make the bromine, Br2 FeBr3. We've seen that many times already. I can make this compound from the appropriately shaped 4-carbon alcohol. PCC will give me the aldehyde. First step here is magnesium to make my Grignard. Second step is to use the aldehyde I just produced. And the third step is mild acid workup. The fourth step is probably, let's use the Swern again to avoid using the chromium reagents. And that will allow us to make this CC bond right here. And the final step oxidizes the newly formed secondary alcohol back to a ketone. So now I have my ketone product on here. I can create that, turn that into the 2-carbon alkene with the appropriate Wittig reagent. And of course, my rules on the first slide of this video should have stated that I can use Wittig reagents that add up to 4 carbons. And I can make this Wittig reagent from ethanol by converting ethanol to a good ethyl bromide leaving group. And I can use triphenylphosphine as a nucleophile. And then I can deprotonate that, often using T-butanol or butyl lithium. And then I have my Wittig reagent, which can be used to create this alkene. And then as I reflected, this alkene will be reduced if I don't sort of protect it or mask it in some way. So I'm going to add an alcohol to the outside edge of that alkene, allowing me to have regio control over the final elimination step. So I'm going to use hydroboration oxidation. And that's not H2SO4, that should be H2O2. And that gives me the alcohol on the outside edge of my alkene. And then 2 steps. The first step is hydrogenation, palladium, something like 300 atmospheres of pressure. So a lot of effort goes into hydrogenating a benzene ring. It's not something we do all the time, but if we have to, we can get a 6-membered aliphatic ring from a benzene ring. And then second step would be to tosylate my alcohol, and then I want to eliminate towards the more substituted side, so let's use the smaller base. We can use ethoxide in this case to basically turn this alcohol into the more substituted alkene, giving me my final product. That's the finished synthesis. As with all synthetic problems, we should always be on the lookout for places where our reaction may react to produce potential byproducts. And I think I've avoided a lot of that here. We should also consider, could I make this using a different pathway? And as I look at this, observing this alkene, what if I used a Wittig to install this alkene as the last step? Then I would need a carbonyl here. I'd probably have to protect the carbonyl during this harsh reduction step. So let's look back, and I'm going to switch to green here. I think I could use this carbonyl in a slightly different manner. So if I can make that carbonyl, let me redraw it. And if I want to use that ketone as in a final Wittig reaction, I need to first protect it so that it doesn't go away when I reduce the heck out of my benzene ring. So I can make a cyclic ether, like this, and then I can reduce the heck out of this compound, H2, palladium, 300 atmospheres. And that's not it. Let's erase that. I can expose the protecting group with water and acid, and that will get me to this compound. And then I can, to follow the green arrow here, I can use a Wittig. I'm not going to write it here, I'm running out of room, but of course it's the same Wittig I used down here. Except that would be my final step instead of sort of in the middle of my synthesis. So if I can preserve this ketone until the very last step, then I can use a Wittig to install this alkene. And that actually might cut down on some steps. Let's look at this. So from this ketone, I used a Wittig, hydroboration oxidation, then a reduction and elimination. So I'm sort of 4 steps from the product if I start with this blue ketone. If I start with the same ketone in green, I have to protect, then I have to reduce, which gets me here, then I have to deprotect, then I have to use the Wittig. So that's also 4 steps. Sometimes you might fudge it and say that the protecting and deprotecting are not quite steps, but they still take time in the lab and purification. So I'm not sure this is any more efficient. It just might be a different potential pathway, sort of a rearranged version of what I originally did in blue over here. So just a few more thoughts on this product. This 6-membered ring came from benzene. So whenever you see a 6-membered ring using the same rules that we've already established, using alcohols that contain between 1 and 5 carbons, you might consider starting from benzene and putting some groups on benzene and then reducing that benzene all the way. So you could envision a 1,3 substituted cyclohexane ring coming from a meta-substituted benzene ring, or a 1,2 substituted cyclohexane ring coming from a ortho-substituted benzene ring. So we see here that we can use benzene, which is an allowed starting material, as a source of 6-membered rings, even as aliphatic rings. So that can be another synthetic strategy that you keep in mind as we go about this. All right, let's look at this molecule. We have a long carbon chain. We've got a carboxylic acid on the para position, and then we have what looks like it's not a aromatic ketone, but it's a ketone that's on the carbon chain only 2 carbons away, or 1 carbon away from the aromatic ring. I can think of a few ways to make this carboxylic acid, and I want to start with one way, and then we'll come back to this and consider another way. So what we can do, if we have a Grignard in that position, and I hope you'll all agree that it is actually pretty simple to put a Grignard in that position. I'm going to protect this carbonyl. I can add carbon dioxide as a source of my 1 carbon and couple of oxygens. After protonation, I have a carboxylic acid. So this is one option. And of course, I can create the Grignard from the bromine, or I could even consider, actually I'm going to consider that alkyl group to be an ortho-para director. So I'm going to have that, and then I'm going to turn that into my Grignard, because I think if I put 2 Grignards on this ring, it's going to interfere with each other. So I'm going to put 1 Grignard on to make this compound right here. Then I'm going to use the other Grignard, as you saw, to make the carboxylic acid. And I can make this compound. The important thing to notice is that the carbonyl is on the second of the carbon chain that's added. So that's very indicative of an epoxide ring opening via a Grignard. So let's go ahead and look at that Grignard. And of course, if I open an epoxide, I can then oxidize the alcohol to make my ketone. So what if I had this Grignard and this epoxide? Let's see how many carbons I need. And I need 7 carbons, so I have 2 of them. So here's 3, 4, 5, 6, 7. And now the challenge is making, certainly I can make the Grignard from benzene, so I'm not going to worry about that any further. How do I make this epoxide from 5 carbons or less, chains of 5 carbons or less? Of course, that epoxide comes from this 7 carbon alkene. If I make this carbon right, or this bond right here, that is starting with 5 carbons and 2 carbons. So that would fit my allowed parameters. So how could I make that bond? If I had that alcohol, I could make that alkene, and I could make that alcohol from a Grignard reaction between those 2 species. And of course, I could make this from ethanol, and I could make this Grignard from the 5 carbon alcohol. So I think that's one pathway. So let's fill in the blanks here. I can make the Grignard obviously with PBr3. That's first step. Second step, Mg. I can make the aldehyde with PCC. This is called acetaldehyde. And then of course I can take these 2 and I can mix them together, and I can use mild acid to work up that reaction to get me to the alcohol. I can eliminate that alcohol, tosyl chloride, pyridine. And second step would be a large bulky base so that I can get as much of the Hofmann elimination product as possible. And then of course MCPBA will get me to the desired epoxide. I can make the Grignard aromatic ring. We've seen this already several times on this video. Br2 Fe Br3, that's the first step. Second step, just add some magnesium. Then I can mix these Grignard and epoxide together, and I can do some mild acid workup, because I would get let's see, this carbon would be where the alcohol forms, and then of course I can use swern to oxidize that alcohol to get my ketone. I can protect my ketone. We've seen this on every video in this, or every problem in this video. So protecting the ketone is not too much of a big deal. Then I can make another Grignard. With magnesium. First installing the bromine in the para position, then adding magnesium, and then that Grignard can react with CO2 to add one single carbon, leaving us with a carboxylate that I can then protonate under mild acidic conditions. In fact, if I make this strong enough, H2SO4 and water, I might be able to deprotect and protonate my carboxylate at the same time, so I can save a step that way. So I think this works pretty well, and should allow us to make this, this compound. Let's think of another way to put that carboxylic acid group right there. Can we do that? Remember the Baeyer-Villiger reaction will take an aldehyde to a carboxylic acid, and actually that can be quite useful, because if I wanted to use, say, let's say I had this compound and I wanted to oxidize it. I could use the benzylic oxidation reaction. However, I have two benzylic positions. Probably both would get oxidized. I'd cut off this chain that I so painstakingly installed down here, and I'd end up with a dicarboxylic acid, which would make me rather unhappy. So let's not do that. Let's use a technique we saw on the first one of the videos, the first problem on this video. We protect that, and we have an aldehyde here. We could make that via MCPBA, a Baeyer-Villiger reaction, turns our aldehyde into a carboxylic acid. And then step 2 would be deprotection. And let me try to be a little less sloppy here. Deprotection of our protected ketone. And of course I need to protect my ketone because the Baeyer-Villiger will also react with this ketone, and it would give us a mixture of products because both of these carbons would be likely to migrate equally. Whereas over here, if we attack the aldehyde, the H is much more likely to migrate than the phenyl ring. So that means I need to be able to get here, and I can get to this compound, I think, by keeping this group protected, using a Grignard right here and adding formaldehyde. So let's try that. What if I had this compound, which I've already made, so I don't have to show you how to make it. And I could add, first step, 1 carbon aldehyde. In the second step, I could use, let's use some ammonium chloride to make sure that I don't deprotect yet. And then 3 would be oxidation of that aldehyde. Probably, again, I want to use the swern to make sure I'm not using any chromium reagents. Again, I've got a benzylic position, and actually this will become a benzylic position too. So I could end up with 2 carboxylic acids on my ring if I'm not careful with my oxidation conditions. But I already made that here, and so I don't necessarily need to show how to make this compound. So this is just a different route from here. We could take this 2-step route instead of sort of this 1-step route. And maybe you choose that because, I don't know, you didn't have a source of CO2 handy, or you just wanted to use the Baeyer-Villiger reaction because you thought it was really cool. Really, it's up to you. So with these open-ended synthesis problems, there's often many ways to solve them. And there's probably a couple more ways that I haven't listed on this slide. If I took a few more minutes, I might be able to think about them. But perhaps you've thought of something, and if you think it's right, but you're not sure, bring it to my attention. Draw it for me and show it to me, and we can talk about it.